object, and then lesioned out different kinds of sensors. So our robot has 4 different kinds of sensors: touch sensors in the feet, angle sensors in its spine, so it can tell how the spine is actuating, distance sensors, so it can tell something about how far away from the block it is, and also orientation sensors, so it knows how it's oriented relative to gravity in these virtual worlds. If you look at, in this grouping here, the end grouping, this is no scaffolding here, the leftmost bar. Between scaffolding next to it and then the dark gray bars are where we incorporate both evolution and development. If you lesion the touch sensors, the behavior is completely destroyed. The robot doesn't move at all or thrashes in place. So there's 100% performance impact if you lesion touch sensors. So touch sensors, you can't do without them. Whatever oscillatory behavior or internal dynamics the evolution is discovering for the controller, it depends on the touch sensors. Okay? If you leave the touch sensors intact and instead lesion the distance sensors, you see a different pattern. So here is just between scaffolding and within scaffolding regimes. Remember, we only have one phase of the no scaffolding situation. So in the evolved controllers that start prone, okay, on average, they rely 60% on the distance sensors. So some evolved solutions depend on it completely, other evolved solutions don't depend on it at all. The reasons why it doesn't have to depend on the distance sensors completely is because we always put the block in the same case. So sometimes it learns blind locomotion, and in other cases it learns taxis. It learns to actually approach the object based on what the distance sensors are saying. As we then move from the prone stance up to evolved solutions with increasingly high centers of mass, it starts to depend on the touch sensors slightly more. So you see this gradual increasing dependence on the distance sensors. You see the same things if you leave the touch and distance sensors intact, but instead lesion the angle sensors, until when the robot is upright, most of them are depending very heavily on the angle sensors. Okay? And finally, the same situation with the orientation sensors. When the robot is prone, not surprisingly, it doesn't depend on the orientation sensors very much because it's impossible to tip over. Okay? You only need to pay attention to your orientation sensors if there's a danger of falling over. Right? It tends to use it a little bit, but it's not that important. And then again, that dependence grows rapidly over time, and the rate of increase in dependence is most pronounced for the orientation sensors. So in the case of the distance sensors, it goes from 60 to 80% dependence, so it becomes about a third more dependent. Same thing for the angle sensors, but there's an over 50% increase in reliance on the orientation sensors. The reason why is that as the evolved robots transition through these different body plans, falling over becomes increasingly common and more dangerous. So what happens down here is the controllers or evolution masters displacement first and ignores keeping one's balance, but then gradually incorporates this fourth sensor modality to allow it to displace while staying upright. So the scaffolding here is basically allowing it to capture or succeed at different parts of the task, right? Legged locomotion requires displacement while keeping one's balance, okay? So the body plan is in essence implicitly breaking the problem up in these two sub-problems. Okay, I'm going to wrap up here. I think I'll skip that and just summarize what I've talked about here. As we know, embodied cognition challenges us to think carefully about not just the control policy, but the task environment. Most importantly, the body, but which body should we be focusing on, right? How do we choose a body given a desired task like object manipulation, active categorical perception, legged locomotion? I would argue that often what we do is jump to the wrong conclusion, which is this is the right body plan. Here's a quadruped or a biped that is very similar to a human or a quadrupedal animal, and therefore we're going to have a better chance of realizing legged locomotion. Rather, we should think about what are the changes in body plan that body plans that we might want to replicate. So I showed you how that works in object manipulation. So as the task becomes more difficult and we can tune the difficulty of the task, it becomes increasingly useful to evolve or change the body plan. That's now online as an Artificial Life journal article. I then switched to legged locomotion and showed you that if you incorporate a very simple model of evolutionary change in the body plan and a very simple model of development, you can actually realize your end goal of legged locomotion in an upright quadruped faster than if you disregard either of those two processes. Again, the background material and motivation for a lot of this work you can find in the book that Rolf and I co-authored. I think I'll stop there and take questions. Thank you very much.